All right, in this case, we see a soap bubble sandwiched between air. And so in that case, we're going to see two boundaries, one from air to soap and soap to air. So the first boundary, wave A, reflects off of, and the second boundary, wave B, reflects off of. So the first question is, what is the equation for the total phase difference between wave A and B when they both exit the soap bubble? So the key here is to look at the different indices of refraction for both air and soap, because when concerned about the total phase difference, we are also concerned about the phase shift. And the phase shift picks up a factor of pi, reflecting from a lower index of refraction off a higher index of refraction. It does not when reflecting from a lower index of refraction, from a higher, index of refraction off a lower index of refraction. So in this case, the index of refraction for the air is 1, which is lower than the index of refraction for the soap, which is 1.42. So in this case, wave A is going to pick up a phase shift of pi, whereas phase B, going from soap to air, or soap off of air, will not pick up that phase shift of pi. So in that case, that is the change in their phase shift. So our general equation is the total phase difference is k times delta x plus the difference in phase shift, so that is k times delta x plus pi. The second question is, if we see a green light in the air, so a wavelength of 550 nanometers, and it's implied that the wavelength is constructively adding, we want to then determine from that the delta x, so the minimum distance that the soap bubble would be. So in this case, the first thing we need to do, the phase shift that we got in part A, the general equation for that, we can incorporate a lambda term into that, the wavelength. However, it will be in terms of the soap. So the first thing we want to do is convert the wavelength in air to the wavelength of soap. So the wavelength of the air is 550 nanometers. And so we know that the index of refraction in the air times the wavelength in the air equals the index of refraction in the soap times the wavelength of the soap. So in that case, we have 3 constants and 1 unknown, so we can just solve for the wavelength in the soap, and that is 387 nanometers. We're then going to want to plug this back into our general equation for the phase difference, where k can be written as 2 pi over wavelength. So we have 2 pi over the wavelength times delta x plus pi, and we know it's constructively adding, so that equals 2 pi times m. We are looking for the minimum thickness d of the soap, so we can set m at a minimum, which would be m equals 0. So we can set that whole side of the equation equal to 0, so we get 0 equals 2 pi over 380 centimeters, our wavelength, times delta x plus pi. We can just rearrange that to solve for delta x, and we get 193.5 nanometers. The objective for this question is, I understand and can use in calculations the requirements necessary for waves to constructively or destructively interfere.